All right, and so it's this little marginal difference in this case because these aren't very different masses, you know. So they really should do the 1 to 5 or 1 to 10 ratio. That would be the ideal, and then they could show this creation of twice the, 3 times the energy, 100 in, 300 out. But just absolute crap. So let's do.
And here we are once again with another elastic collision experiment. This time the mass ratio is 1 to 10. So this is quite a big boy now with a lot of mass attached on it. All right, let me show you the masses. So I'm going to weigh them. This one is still 33 grams. 33, so times 10 is 330 grams. 330.6, so pretty much almost perfectly 10 times the mass. So now this is a heavy boy, creating a lot of pressure on the surface of the track. So a lot of friction at play. The slower it goes, the more friction and the more we will lose momentum. So I'm going to try to put in high velocities. If I'm doing this slowly, it barely moves. So I'm going to have to push this one pretty hard to make it go quite fast, to make sure that we lose as less momentum as possible. So, okay, this time I'm going to record it from the front, so to give you another perspective. If you want to do analysis, if you do not trust the timers, you can try to do, I don't know, count the frames or whatever. Okay, so first trial, let me turn on the timer. There we go. Okay, let's see. So the 10 mass came out with a timing of, let me do this, timing of 0.1242. The reflection of mass 1 is 0.0265. And it came in with a timing of 0.0199. All right. Again, a reset. Second trial now. This one over here. Reset the timings. Okay. All right. The reflection, mass 10 came out with a timing of 0.1273. The reflection of mass 1 is 0.0273. And the incoming timing of mass 1 is 0.0212. All right, trial 3. This one back. Reset the timers. Reset. Okay. Okay. Mass 10 came out with a timing of 0.1251. The reflection of mass 1 is 0.0253. And the incoming velocity, the incoming timing of mass 1 is 0.0207. Let's do another one. Right, turn on the timers, here we go. Okay. All right, so the mass 10 came out with a timing of 0.1145. The reflection of mass 1 is 0.0262, and the incoming timing of mass 1 is 0.0200. So now I'm going to do the calculations. Okay, let's check out the calculations. I've written everything down. You can read it if you want. I'm going to talk only about momenta. So the incoming momentum was 0.03316 for trial 1. Then the mass 10 came out with momentum of 0.05313, which means that we already have 60.22% more momentum than the initial total momentum. So according to draft science, this is already a free momentum experiment. We have 60% more momentum than the initial total amount of momentum that went into the system. Now, if we subtract these two, if we subtract it with the momentum going in the opposite direction, then we have actually lost, I have lost 14% of momentum, which is, I think, makes sense because now it's 10 times as heavy instead of 5 times as heavy. And so the heavier it gets, the more friction there is and the more momentum that we will lose. Now, for draft science model, it's not looking very good because now we have to add these two together, which means we have 135% more momentum than the amount of momentum that went into the system initially. 135. So as we can see, if we compare this with the previous experiment, with the 1 to 5 mass ratio, we are losing more momentum for conventional science, and we are gaining more momentum for draft science model. So this works inversely proportional. So the second trial, the initial amount of momentum is 0.03113, and then the 10 mass came out with 0.05184, which means we have gained 66% more momentum than the initial amount of momentum that went into the system. Now, if we subtract this the opposite direction, for conventional science, we have lost 11.28% of momentum. For draft science model, we have gained 144% more momentum than the initial momentum. 144% more momentum. Trial 3, the initial momentum that went in is 0.03188. Then the 10 mass came out with 0.05273, which means we have gained 65% more momentum than the initial amount of momentum. So for draft science, this is already free momentum. 65% more momentum already. So now, according to conventional science, if we subtract both momenta, we have lost 16.41% of momentum. For draft science, if we add them together, we have gained 147.21% more momentum than the initial amount of momentum. Trial 4, the initial momentum that went into the system is 0.033. Then the 10 mass came out with 0.05761, which means for draft science we have already gained 74% more momentum than the initial amount of momentum. If we subtract the momenta, we have lost, this time, we have only lost 1.73%. So this last trial is seemingly the best trial out of all 4 trials. Only 1.73% loss of momentum. Now, as you can see, for draft science, we have gained, if we add them together, we have gained 150.88% more momentum than the initial amount of momentum. So as you can see, the less error percentage we have for the loss of momentum, the bigger the increase of momentum for draft science model. Okay, so the less momentum we lose, the more this approaches 0, the more this increases, the better it gets for conventional science, the more of a free momentum experiment it becomes for draft science model. Strange, isn't it? Only when we subtracted, the less worse the error percentages will become. When we subtract it, when we add them together, we have insane increases of momentum. There you go, people. Once again, draft science model fails for conservation of momentum.